Okay, let's get started, please. So, remember what we finished up with last time, where was the two forms of Green's theorem. Two forms of Green's theorem. And there's one called the circulation curl form. It's like this, that if you take the circulation of the field around a curve, right? A closed, simple closed curve. Then that's the same thing as taking the integral on the interior of that curve of the scalar curl. Right. So this was this thing here we call it the scalar curl. Right? And this whole thing on the left here is called the circulation of the field. Okay, so that was the first form of Green's theorem that we saw. And then we said that there was a second form which said the following, that if you take a field and you dot it against the outward unit normal vector, again over the boundary, right? Then it turns out that that is equal to the integral of the divergence of the field on the interior. Let me say one thing about the outward unit normal. So it's like this, right? You have some loop, right? The interior is D, the outside is C, the boundary, and you're oriented in the positive direction, right? T, if we let T be the unit tangent vector, right? T of T. Let's say that T of T looks like this, x, y. Okay. So it's right, some tangent vector, and you see how it's going. Because you're going in this counterclockwise way, the unit tangent vector is going to be unit vector that's tangent to the curve, right? Right. So you have this guy here. This is the unit tangent vector. Right. Then the outward normal vector is the outward unit normal vector is going to be this one. Yt negative xt. Y of t negative xt. Right. So this thing, what it's supposed to be is, it's going to be perpendicular to the tangent, and it's going to be pointing outwards. Right. So it should, geometrically, it should be this guy, right? Outward unit normal. Okay. And so, you see how we make it, right? You take, we create it so that if you take the dot product of these guys, you get 0, right? Because you're going to get this function against this function plus this function against this function, right? So clearly we've created it so that they're going to be orthogonal to each other, right? So you know that the way we've written it, nt is going to be either this guy or this guy. So the only thing you're worried about is this going in the right direction? Right? Is it the outward? Did we get the right guy? We found something that's perpendicular, but is it going outwards or is it going inwards? How do you think we should check if it's going outwards or inwards? Here's one idea. Okay. Oh no, I'll let you think for a couple more seconds. Okay, so here's one idea. What you could say is, well, let's think of this thing as an R3, right? What we want is that if this guy is the outward guy, then when we take the cross product, we should get something going in the z-axis direction, right? In the positive z-axis direction, right? And so let's make sure that we do, right? So you say, okay, let's take the cross product. cross product of these guys, right? N cross t. N cross t gives us y negative x 0, x y 0. And you see that what you get is 0, 0, y squared minus minus x squared. So x squared plus y squared, which is good. Okay. Right. So that gives us, that shows that n cross t is going upwards, and so it looks like we do have the right direction for the unit normal. And if we had, you know, we could just as well have, we might have chosen this guy, right? That was also a possibility, because that's also perpendicular. But when you try that, you see that you get negative x squared minus y squared, and so it's going. That would be the inward normal. Okay, just on how you get that unit normal. Okay. 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 So we have Green's theorem, and we also have Green's theorem. We've got these two Green's theorems, and we talked about why the first one is true. Why the second one is true, it turns out that you can just take the first one and turn it sideways, and you get the second one. Okay, so think like this: proof of form 2. You say, okay, well, let's say that f of xy is p of xy, q of xy. Suppose f of xy is p of xy, q of xy. Create a new function. Create a new field. G of xy is going to be negative q, comma p. Okay. And you see that this field that we created is perpendicular to the other one. Now, we proved already the first form of Green's theorem, so apply Green's theorem 1 to G. Right? Let's apply the first Green's theorem to G. Right? That says G dot the tangent vector ds equals the scalar curl of G dA. Right? Remember that taking the integral of a vector field was the same thing as taking the integral of this function, right? Taking the integral of a vector field was defined as taking the line integral of the function that you get by dotting the field against the unit tangent vector, right? So. Okay, right? Okay, so let's see what that is, right? What is G dot t? You think about it, right? G dot t is going to be negative q p dotted against x of p, y of p. Right? So it's going to be negative q x plus p y. Right? But that's the same thing as f dotted against n. me write this without the x's and y's just to make it clearer. Right? We have here g, right? G is negative q comma p, and we're going to dot it against t, which is x comma y, x of t, y, t. Right? So we get negative q x plus p y, right? But that's the same thing as pq dotted against y negative x, right? pq dotted against y negative x, which is n, right? So that's f dotted against n. Okay. And then similarly here, if we take we think what's del cross g, right? What's del cross g? Well, you've got ijk, d1, d2, d3, and then g is negative q, p, 0. Right? You see what you get, right? You get negative q xy, p xy, 0, right? And see what happens, right? You get 0 minus 0, right? You get 0 minus 0, and then the last thing you get is d1 of p, d1p plus d2q, right? But what's d1p plus d2q? That is del dotted against f, the divergence of f, right? You take the partial of the first guy with respect to the first variable plus the partial of the second with respect to the second variable, right? Remember what divergence is, right? So that's, this last part here, this thing here is del dot f, right? And so when you take this thing and you dot it against k, you pick off this thing here, which is the divergence, right? So this thing, what we see is that f dot n ds c equals del dot f dk. Okay, which is the flux divergence form. Okay, so if somebody says, why is the flux divergence form true? You say, well, just take your field F and then rotate it 90 degrees and apply the circulation curl form to that new field. Apply the circulation curl form to that rotated field and see what it says. The circulation curl form says that this is equal to this. But if you do the calculation, this thing, the circulation of the rotated field is the flux of the original field. And the curl, the integration of the curl of the new field is the divergence of the old field. So the divergence of the original field equals the flux of the original field. Okay, so you get the form 2 by just rotating form 1. Okay. Any questions about that? Any questions? Ask if you have any questions. Anything confusing? Right. We're trying to show, right? We already showed this one, or at least we gave some idea as to how it works. We're wondering why this one is true. Right? We say, okay, well, let's see if we can show that flux is equal to the integral of the divergence. Take your field, rotate it, apply the circulation curl field to that one, and it shows you that flux equals divergence. Okay. Okay, so that's that for section 17.5. Now we're going to go into, we're basically going to go one dimension higher. Okay. 17.6, parametric surfaces. Okay. So just like you have parametrized curves, right? We spent the first third of the course talking about parametric curves. You can also talk about parametric surfaces. Okay. So let me put up the definition. So you have some D a region in R2, and you have a function R going from D into R3. Where, say, R of UV is X of UV, Y of UV, Z of UV. Okay. So here's the picture, right? You have some region. Let's make it doesn't have to be square. You have some region in R2, right? And then you have some map of that guy into R3. Okay, and so you have this thing, and it turns out it turns into some sort of two-dimensional thing in R3. Okay, so here we are in R2, it maps into R3. Right, just like previously, how our parametric curves went from R1 into R2. Right, you had some AB here, and R mapped that into a curve, right? Into a curve, and this was the parametrized curve. Here, this thing is the parametrized surface. Okay, so it's just one step up. Okay? So the image of R is called a parametric surface. Or another way of saying that is that R is the parametrization of that surface. Okay, so some examples. If we let R of UV be cosine U sine U V, then what is that? Let's say that U goes from 0 to 2 pi, and V is any real number. Okay. So R is U is V, right? 0 to 2 pi, right? So U is between here and here, and V is from here. Okay. Right. What does that look like? Can anyone tell me what the image looks like in space? Well, think of what happens if you hold a V, right? You fix V, and then you just let the U vary. What are you going to get? You're going to hold it at a height, and you get a circle, right? Right? And so at every height, you get some circle. And so what this is a bunch of circles on top of each other. Right? For every fixed V, we get a circle. Right? Or conversely, for every fixed u, if we let the v's vary, then they just go up and down. Right? Right. So this thing is a parametrization of an infinite cylinder. Okay. Number 2, let's try this one. R of uv is v cosine u, v sine u, v. Okay, and we'll use the same domain. So again, uv lies in 0 to pi cross r. Peter?
Would it be like cones going through?
That's right. Yeah, it'll be a cone. Right. So again, right. So you've got your this domain here. Right. R goes this way. Right. For each fixed v, we're going to have. For each fixed v, you're going to have a circle of radius v, right? You're going to have a circle of radius v. Even if it's a negative number, that's still going to be a circle of radius v. Right? And so you just get a bunch of circles where the radius of the where the radius of the circle is the same thing as the height. So if I'm here, the radius is going to be that. Radius and height should be the same. So you got this cone going down as well. Right. So this is again parametrization of this surface. Okay. Last one. R of uv is sine u cosine v. Sine u sine v cosine u. Okay. And v goes from 0 to pi, and u goes from 0 to 2 pi. So you've got this, you've got a map from u v 2 pi pi, right? From this rectangle, and this rectangle maps to something in space here. Does anyone recognize it? Do you, Paul? What is it?
Would it be a half a circle?
It's actually a full circle. I mean, a full
sphere.
Yes, it'll be a full sphere. So, right, these are from the Cartesian form of the spherical coordinates. Right, you remember that x was r sine theta cosine v, y was r sine theta sine v, and z was r cosine theta. So this is going to be a sphere of radius 1. Okay, which is pretty cool. Right? We have this parametrization of the sphere, right, going from this rectangle to the surface. Any questions? Any questions? No? Okay. So, okay. 0 is here, right? Okay, so there's one case where parameterization is really easy. Okay. Here's an easy, simple case. Right. Maybe finding parameterizations in general may not be so easy, but there's one case where it actually is really easy. The graph of a function. So graphs of a function. Okay. So, right. So somebody gives you a function on a region D in R2, from R2 to R, right? And says, right, I'd like you to, here's the graph of the function. Let's call this thing gamma. I'd like you to find a parameterization for gamma. Okay. So, so it's easy, right? So here's the graph. Right? The graph is x, y, z, where z equals f of x, y. Right? If somebody wants you to parameterize it, it's actually easy. And you say, well, just take r of x, y to be x, y, f of x, y, where r goes from D into space. Right. Here's your graph. Right. Here's your graph, and you say, okay, well, I'm just going to take as my domain. I'm going to take D. And I'm going to create R by saying, you know, this point xy is going to go to xy, f of xy, right? That's the obvious thing to do, right? And that gives you a parameterization. Okay. So parameterizing the graph of a function is very easy. Okay. Let me. Some examples. So for example, if somebody says, please parameterize the lower half of the ellipsoid 2x squared plus 4y squared plus z squared equals 1. Say, well, I know that z is going to be negative the square root of 1 minus 2x squared minus 4y squared. Right? So you just take, so r of xy being x, y, z will do. That gives you your parameterization. Another example, parameterize the part of the circle, the sphere, of radius 2 that lies above z equals root x squared plus y squared. Maybe I'll let you try it. Take 1 minute and see if you can do it. Okay, turn to somebody next to you and talk a little.
Would you do like z equals negative square root x squared plus y squared plus 4 or and then subtract
I know, because of
the second part?
So you mean it would be like x, y, comma, that whole thing minus that?
Yeah.
I don't know.
I don't know.
Radius
Rise
is
above.
That's my best.
Yeah.
What did you?
Okay, anybody have ideas? Anybody have some ideas? Alana, go ahead.
So would it be x, y, and then solve the first part for z and then
Yes.
subtract
Yes.
the second part?
No, not quite. But close. But close, right? So you've got all they're asking for is that you parametrize the part of the sphere that lies above this cone, right? So you have this cone here, right? And they're asking you to parametrize this cap, right? Just this cap here. Okay, so you don't need to subtract off. You don't need to subtract the cone or anything like that, right? Rather, you say, okay, right, this thing is going to be x, y, z, right? Z is going to be the square root of 4 minus x squared minus y squared, right? So that's z, and then the only thing you have to worry about is, what the domain is. So you just say, well, what's the domain going to be? The circle, the disk of radius 2 down here. Right? So this is over where d equals xy, where x squared plus y squared is less than or equal to square root of 2. No, 2. 4. What am I saying? We want, so this is going to be 2, so this is 1 over the square root of 2, right? Sorry.
How'd you do
No? Right, a squared plus a squared is going to be 4, right? So a squared is equal to 2, square root of 2, sorry. Square root of 2.
If you're looking for the part that lies above the cone, how come it's just like the cap? Why isn't it like the whole?
Because we're saying equals 4, so this is just the shell. This is not the full
Oh, okay.
thing,
Okay.
right? It's not a solid. It's just this.
Just the outside.
The top
Okay.
surface.
But it says lies above a part of the cone, but aren't they like the same line? Aren't they one? It's not above it, like it's just that part of the cone is that part of the shell.
No, right? You've got, right? I think you have a ball here,
Mhm.
right? And then you have a cone inside the ball that comes out like this, right? And that cone chops off some part of the ball,
Mhm.
right? And we're talking about that part that gets chopped off.
Okay.
Okay. So enough of that. Next idea, tangent planes. Tangent planes to parametric surfaces. So first, observe the following. If you have a parametrization R 3 as before, taking uv to x of uv, y of uv, z of uv. And you fix u naught. Okay. Fix u as u naught. Okay. Then, of course, that gives you a parametrized curve. Right, a parametrized curve on the surface. Right, the curve where v varies. Right, you guys see that? Right, you have some domain. Say, here's your domain, uv, right? That is mapped into space, into some, line carpet in space, as always, right? If you fix u naught and let the v vary, right? What you're gonna do is get, some line, right? You're gonna get some parametrized curve in space, right? So if you fix u naught and just map from this line here, right? Then r u naught comma v, right? U naught comma dot is going to map onto some curve that lies on the original surface, right? And you can do the opposite, right? If I fix v naught and let the u's vary, then I'm going to get some other curve, right? Going like this. Okay, so right. So for example, if we call R of R of, say, theta phi, we let that be sine theta cosine phi, sine theta sine phi, comma cosine theta. Is that right? Somehow that doesn't look right. R sine theta, R sine. That's wrong, actually. Sorry. Right? It should be. It's backwards. Sorry, I wrote it backwards the first time. It should be. Sorry. It should be cosine theta sine phi, sine theta sine phi, and then cosine phi. Right. Yeah. Sorry. So what I wrote up earlier, I fix it. It was wrong. Okay, if we have this thing, which is the parametrization of the sphere, right? If we fix, right, what kind of curves do we get? What kind of curves do we get? If we fix the theta and then let the phi vary, what do we get? We fix the theta and let the phi vary. Well, do you remember what the phi was? The phi was the angle from the top, right? So if you fix right, so the theta is telling you, right, where you are this way. You fix the theta and let the phi vary. That's going to give you vertical lines, right? It's going to give you vertical lines down the sphere. If conversely you fix the phi, right, and then let the theta vary, you're going to get latitudinal lines, right? So you get, the first one gives you longitudinal lines, the second one gives you latitudinal curves. these guys are for fixed phi, right? And then these guys vertical guys, are going to be for fixed theta. Okay. Okay. So in the text calls these guys, these curves, grid curves. Okay. I've never heard this term outside of this text, but so anyway, in this text they call them grid curves. Yeah, I mean it's a logical name. Okay, so how do you think we get the tangent planes? Does anyone have an idea? Suppose somebody says, "I'd like to get some tangent planes to this curve, to this thing, right? I'd like to get a tangent plane here." How would you do it? What's the tangent plane to the sphere at that point?
Do you take partial derivative?
Exactly. Great.
Of the partial derivative of that curve,
Mm-hmm.
like the latitudinal way and the longitudinal way at
Yeah.
that point.
And then?
And then add them? No.
You wouldn't add them, but taking the tangent vectors would give you these two. Would give
cross
you.
them.
You take the cross product, and that would give you the normal vector, right? Once you have the normal vector, then you can figure out the tangent. You know the position and the normal vector. That's enough to give you the tangent plane. Great. So let's say, okay, suppose you want, so getting tangent plane. Say at the point theta naught, phi naught. Okay. So you'd say, well, I'm going to take the partial of the first with respect to one variable. I'm going to take the partial with respect to the other variable. Right. These guys are tangent vectors. To the sphere, to the surface at r of theta naught, phi naught. Right. So if you take the cross product, that's a normal vector. This is a normal vector. To the tangent plane. Okay, great. Okay, so for example, somebody gives you this parametrized surface, u v goes to u plus v 3 u squared u minus v, and gives you a point, and says, what's the tangent plane at this point 2, 3, 0, which you figure out is r of 1, 1. Okay. You say, well, all you need to do is take the partials at 1, 1, right? So you take the first partial and partial with respect to u, right? So that's going to be 1, 6u, 1, and you evaluate it at 1, 1. That's going to be 1, 6, 1. You take the partial with respect to v, and you evaluate it at 1, 1. That's going to be 1, 0, negative 1, which evaluated anywhere is going to be 1, 0, negative 1. Right? And then you take the cross product, so you take then 1, 6, 1 cross 1, 0, negative 1 turns out to be negative 6 to 6. I'm sorry, negative 6 to negative 6. And then, so you use the point, right? You have the point, and you have the normal vector, right? And so those two things together give you that negative 6, x minus 2, plus 2, y minus 3, minus 6, z minus 0, equals 0 is the tangent plane. Okay, so we're moving into, we're talking about parametrizations of surfaces, right? So we have these surfaces in space. What we're going to do soon enough is take integrals on those surfaces, right? So we'll have the surface in space, and we'll integrate on those surfaces. And then we'll talk about fundamental theorem of calculus for integrals on surfaces in space. Okay, and then we'll go one dimension higher after that. Okay? So look forward to it.